Here we go. Cool. So I've sent you a few tasks. So we're gonna look at these solutions now. I've seen some of you done something towards this. But first question, you want to discuss anything about yesterday's patch? Did you have a look at it? Managed to add 4 bandpass filters? Yes or no? Not much. Okay. So we'll do more serious and parallel stuff anyway. So let's get on with this one. So first thing says make an FM patch with 2 modulators, 1 noise, 1 square wave, and 1 carrier, which is a triangle oscillator. Okay, so we've done some FM already, so it shouldn't be too bad. I'll call it an A for the first modulator, so it will be noise. Now the question is, what kind of noise? Obviously there's a lot of questions. I didn't specify many things. What do you know about potential noise sources?
White noise.
White noise is one of them. Any other ideas? Can we control any parameters of the white noise? Does it have any parameters? Yeah, well, typically what you get is that, you know, the core generator does not have amplitude, comes after, actually. Amplitude is always the multiplier that comes, yeah? Yeah, well, that's an adder that also comes after. So actually there is no valuable controls that would change the character of the noise. We can change the amplitude and we can change the offset. These are the multiplier and the adder. But actually the character of white noise is quite static. So do you remember any other noise sources that we've looked at in the meanwhile? LF noise, indeed. So LF noise comes in 3 types, 0, 1, and 2. You remember what these are?
That noise, ramp noise, and quadratic noise.
Yeah, so what does this mean? Well, stepped noise should be something you can interpret. Can you try and do that for me? What do you think stepped noise means? We've used it yesterday to create the kind of melody line. So it's probably worth looking at it in detail then. So the LF noise, let's start with the 0. This is a step noise. Yesterday I said stepwise or staircase type thing. So you can imagine a staircase visually. And here are the parameters. So what do you think the frequency parameter does? So it gives you the frequency at which a new random value is selected. Okay, so I've talked about noise last year. How do we synthesize white noise? Does anyone remember? What is white noise?
Randomized sign.
Not a sign, it's just random values. Okay, so if you take random values between -1 and +1 and put them into an audio signal, what you will get is white noise. So it's a very simple way to synthesize. So actually all these noise generators, what they allow you to do is set the frequency at which the random value is set. Okay, in order to get white noise, you need to set a random value for every new sample, which means that this should be sampling rate. Okay, so if I set this frequency here to sampling rate, and you remember there was a thing called sample rate.ir. If I set it to sample rate, then I will actually get clean white noise because I get a random value for every sample. Okay. Now what this allows me to do, it allows me to lower the frequency of new noise values such that I get less density in essentially phase turbulence, in phase randomness. So from a very dense noise, I will get a much more sparse noise. And it will actually start to sound, well, it's difficult to describe, but more crackly, more as if it was consisting of larger chunks, which is essentially what it does. Okay, so let's try to listen to that. That could be an interesting thing. So I will run a line from, well, let's pick the sampling rate. I believe I'm on 44,1000. Actually, let's do the neat thing, sample rate.ir. So it's going to be independent of the sample rate itself. And then I'm going to end at 2 hertz. But what I'm going to make sure is that it's an exponential line, right? Because if I run from 44,000 to 2 linearly, then half the duration of the time will be taken to drop to 22,000, which will be hardly audible, right? So I would end up with getting the core difference only in the last few seconds of the run. But if I run an exponential line, then that won't be the case. Then every duration will essentially amount to an equal division. Okay? So I will run it to 2 and run it, I don't know, 20 seconds. Let's see how it sounds. That's my X line. This is the LF noise. That's great. And this is play. Oops, dot play I meant. Okay, and at the end I'm left with 2 hertz clicks. Some louder, some softer. So actually what you get is that every half a second I change a fixed voltage. You might even see if the speaker is DC coupled. And it's not, because now the signal is a stepwise signal moving to a different voltage every half a second. And if the loudspeaker is DC coupled, you would see the membrane come out and stay at a single point. I mean, I can try to, but I'm pretty sure it's coming back each time. So this means that the speaker actually has a high pass filter. It doesn't give you the DC, it doesn't give you the 0 hertz coming through. Okay, so so you remember you heard it kind of suddenly change character, suddenly change character, suddenly change character. So this has to do with the fact that, first of all, as soon as I start changing every sample, to start changing every second sample, it's a sudden drop in quality. And then to change every 4th sample and so on. So if I show you the linearly interpolated noise coming down, what you will get is that instead of having fixed voltages one after the other, you will have a linear interpolation. So they will be connected with a straight line. So initially it will sound the same, and then slowly it will actually sound a bit more rounded, less high frequencies. Okay, and in the end I don't get the clicks because I get really slow straight lines rather than these staircase type things, rather than the jumps. Okay, and then finally LF Noise 2 has cubic interpolation. So instead of being straight lines, it will actually be rounded. So what do you expect in terms of the sound? Yeah, well, it's actually the third one down, right? So we had first the staircase type thing, then we had the triangle type thing, which was already less high frequencies, And then now we will have a more rounded off thing, so even less high frequencies. Okay, so the question then is, which one should we be using here? Any preferences? Well, you see, all three of them do have the same type of parameters, essentially the frequency and the range. How could you argue about this? Come on, guys, you have to say something. Otherwise, I feel like I'm talking to zombies. Why yes, why not? Obviously, we have a sharper version, we have a blunter version, and we have something in between. So how would you argue? What kind of sounds do you expect to get? What is the thing you're after? How about aliasing? Can you bring in aliasing into the argument?
Less high frequencies, less events.
Yeah, the thing about aliasing is that you get it if you get these sharp corners. Okay? So, and in this FM thingy, what we have is already a situation where there's high potential, large potential for aliasing, right? So actually, if we want to avoid too much stuff, then we can probably best use the curvy noise. But the good news is that you can always swap them out. Yeah, you can always change them. Okay, so this is my first modulator then. So I have not specified the parameters, so I can do it myself. Well, let's make it, well, the second one will be to make it audible, so I'll first go with a very slow one. Most nagyon sokáig fogsz még itt pakolni? Mert zavar egyébként. Okay, so the first one, first time around, I'll just make it a very slow modulation, such that we hear it. But the question remains, what will be the range? Okay, so if you try to do this without thinking it through, what you end up getting is a signal between -1 and +1, right? If you don't specify the range, which won't be suitable for a modulator. Okay, so that's one thing you always want to consider. Or indeed, what was the other option that we looked at yesterday? Instead of specifying the minimum and the maximum value, what did we do? We actually did two more things. I spent a lot of time and energy telling you these things. Okay, well, first one I'll repeat. Maybe I don't know what's up. I mean, you're obviously shy to say something stupid, I guess, but it's just horrible. I mean, you know, we've done this last year. We've done a lot of things this year already, and none of this seems to catch on, it seems. So I will repeat, maybe that helps. So the first way of specifying the range that we looked at was setting the minimum value and the maximum value. This we do with the dot range method. The second thing we've done is we've specified a multiplier and an adder. This also changes the range. And by doing that, what we actually do is we specify the extent, the size of the range separately from the offset of the range. Okay, so it's still two values that specify the range, but we grab it in a different way, so to speak. And then the third one, what we've done is we've actually done it with the FM, that we actually made sure that the modulator frequency is related to the carrier frequency and to the modulator depth, such that we have a better control over the sidebands. So in this case, it's still an FM. So that third option might be very interesting and exciting, but I won't go there. I'll try to keep it simple. So I'll just specify the simplest thing, range 200 to 700. Okay, that's my first modulator. My second modulator is supposed to be a square wave. Now, the issue is I have a pulse.ar, which is a band-limited square wave. Who can tell me what's the difference between band-limited square wave and a non-band-limited square wave? So again, it has to do with aliasing.
Filtered and
It's not filtered, because if you filter it, then you lose what you need to start with. You cannot avoid aliasing by filtering. So the only way to avoid aliasing in synthesizing a square wave is to do it by adding sine waves, which is done for you behind the scenes if you use this band-limited pulse wave. However, this will not look like a square wave. So the thing here is that I actually need the LF pulse, because that's what you can call a geometrical square wave. It is actually the one that changes between two values. Because as I want to use it for a modulation signal, I would expect that the square wave jumps between two frequencies up and down. So I will need the LF pulse here. Okay, so again, I'm going to try to make this audible for now in terms of the drift as I specified. So low frequency and the range will be, let's do 600 to 800. Okay, so that's my second modulator. And now, tab. Is my computer dying? I imagine. Funny day. Okay, so those are the two modulators, and then I'm asking for a triangle wave. Well, actually, I will use the LF triangle. For this, amplitude, audio rate, and then I need to specify the frequency. So the question that I expected that you would ask when dealing with this exercise is, how do we combine modulation signals? Okay, so we're trying to have two modulators affect a single carrier signal, which means that I need to combine them in order to put them into this one parameter. So what would be my options? We've looked at different basic arithmetic for combining signals. Adding, or multiplying, or, by the way, we've actually looked even at modulo, I believe, a bit last year. Or we could even do exponentiation. Why not? I can put one to the exponent of the other. Okay, so let's deal with the basic ones, addition and multiplication. What would be the difference if I add or multiply the two modulation signals in this case? So here we have to think about the range minima and the range maximum. A bit of math. Yeah, so I can ask you, if I'm adding the two, A plus B, and these are the two ranges, A goes from 200 to 700, B goes from 600 to 800, what would be the minimum minimum value of their sum. So the minimum will occur when both are at their minimum, right? So this one is at the minimum at 200, this one is at the minimum at 600. If I add them together, I will get 800, okay? Now, what would be the maximum of the sum? Well, that depends on what is the value when both are at their maximum. So that would be 1,500. So you see, suddenly I would get a range between 800 and 5,000. 1,500. Is that okay? I guess. Now, what would happen if I multiply them? Well, the lowest value will be when both modulators are at their minimum, which would be how much? 120,000? Yeah? So it's a bit too much. You agree? I imagine? Okay, so obviously you could think about, I invite you to think about, what would actually happen to the signal, because we could scale it down. But I will keep it simple for now. A plus B. Okay, so this is the frequency of the triangle. Okay, let's hear it. So in this case, I expect to hear, especially if I find the issue here, range, I have too many brackets here, okay. Okay, so what you hear then is the jumps. Okay, that's my square modulator because it just jumps between two values. And then what you hear as well is this kind of change of the pitches inside that, which is due to my LF noise. You see, because LF noise 2 is the curved one, so actually on top of jumping up and down, I'm getting these curves, which are these little pitch shifts type of things. Okay, so the question here is make audible the pitch drifting due to the first modulator only, second modulator only. Well, I could obviously remove any of these to make it obvious that it's just the single one, but I will consider that this example makes both of them audible. You hear actually both modulators. Okay, so now if I start to drive this up in frequency, let's do an xline.kr and let's start at 1 Hertz but go up to 9,000 Hertz for this one and do this in 20 seconds. Okay, I want to hear how these will transform as they go into the audible range. To 9,000, shall we have it different? Let's run it like this for now, and then I will play a bit more with the parameters. Hello? What happened here? X-line, am I just very generous with the... Oh, it's the lowercase l. Okay, that's X-line. So you see, it's actually useful, the fact that you get it colored. So class names always begin with capitals. But I kind of assume that you guys studied the syntax already. Okay, so that's how they combine in the range of frequencies when we don't hear them move, but they actually modulate the spectrum. Okay, let's try it with LF noise 0. So well, I'm kind of bored asking questions. I'll ask it and answer it myself already. So what do I expect from this? Well, because LF noise 0 is stepwise noise, I don't expect to hear the in the beginning, so it shouldn't drift like that. And then towards the end, I expect a harsher sound. I expect more aliasing, more high frequencies. Okay, cool. And then the third one says set very slow drifting noise modulators for all the 6 parameters. So you see, actually, I had 6 parameters here. So I'm going to go back to single values here. So each one of them has 3 parameters: modulation frequency, minimum value, maximum value. Okay, so obviously what I could do is just keep pasting in different LF noises. But let's try to do this in a more interesting fashion. So I've already shown you some array-based processing. Okay, looks like we're back on track. So what I can do then is I can fill an array with 6 noise generators. Okay, so, well, we can do KR. I've asked for slow drifting. So let's do something at maybe 1 Hertz. Okay, and then the question is range. So can I use the same range for all the 6 parameters? The answer is not really if I want slow drifting things, right? So these would be somewhere between 0, well, maybe 1 and 10, 1 and 5 for a slow drift. Whereas these would need to be some interpretable frequency values between 20 and maybe 15,000. So how can I do this? Well, actually what I can do is I'll make a range to start with between 1 and, what did I say, 5. So what I get now is a list filled with 6 noise modulators, and they all go between 1 and 5, which means that I can, this is going to be my R array. So what I can do then is I can say that this one will be R first element. I'm not sure if you've done array indexing with Andras. But what I'm actually doing here is I'm reading elements from the list. Okay, so this will be R2. But now, because I want frequency type values, I really want it to go much higher. So if I multiply this by 20, what will be the range? So the original range is 1 to 5. So 20 to 100, exactly. Okay, so is that, well, it's still a bit low, I could say, right? How about I multiply it with 60? Then it would be 60 to 300, yeah? Still a bit on the low side, maybe. So I'm kind of playing it by ear. What if I do actually 1 till 10? Well, then I get 60 to 600. Still not huge. What I'll do is I'll take 100 here. And then, you see, what I could try and do is make sure that the minimum and the maximum never cross. So I can make sure that the lower boundary, you see the maximum of the lower boundary now is 10 times 10, 100, right? So I can make sure that the other one starts at 100. But in all honesty, it's not even necessary, because if the two boundaries cross each other, minimum and the maximum, then you will just get the oscillator to invert its values. And in this context, it is not an issue at all. So actually, I'm thinking, let's do 200 here to go to 2000. I'm going to do 400. Well, let's do 800 here. So I'm kind of playing it by ear. What I'm trying to get at is variety more than anything. But also, because I have slow drifting oscillators, it's useful to have large range, large wide boundaries, because in that case I can get larger variety of sound. And at this stage I'm actually just interested in exploring that. So let's take, which one should be higher, noise or pulse? Well, actually, if I take rounded noise, I'm happy for this one to be higher. 500. Can I get away with 1,800? Probably. It goes up to 18,000 then. Okay, so you see, I've actually made a list of 6 modulators with a small range. And then when this small range is plenty, I'm using it directly. This is the first element, second element. And then every other element in the list will get scaled up to kind of match a minimum and a maximum value for a frequency modulator. Okay. Quite cool, yeah? A bit of a bird song thingy, you know? So I can try to play with it a bit. I do think there's a lot of very high frequencies going down. So I'm going to drop a bit on these frequencies and maybe even drop it here to a lower range of motion. I mean, it was interesting because actually after 20 seconds, you know, I suddenly get something new, which was part of the idea. But if we push this even lower, probably okay, actually I like the birds better, to be honest, the previous one. But what I'm actually missing here is the noisy character. Okay, it's a lot of just beeps and blips and high frequency oscillations. So how do I add more noise into this? I have a noise generator there already. So if I run this at higher frequencies, then I should be able to get a much noisier thing. That's cool. It's dropping down to 0, 1 here, I guess. Maybe just freaked out. But I think I can get even noisier stuff from this. Let's try it. How is that? Cool. So you can have quite some fun with these things, I imagine. So I think the best thing to do now is to get more coding done for you guys, because it's nice to see this, but I'm afraid you will still need quite some practice to, be able to experiment and discover similar things yourselves. Okay, so I will take this exercise and I will ask you to make a patch with one modulator, which is noise, okay, and two carriers, which would be triangle and square wave oscillator. Okay, so it's similar but slightly different. So let's see how you get on with that. Let's look at the solution together then. Okay, so first of all, a single modulator is an LF noise. Well, actually, I feel like harsher sounds right now, so I'll do the stepwise. And in terms of the modulation frequency, well, we've just heard the one which is slowly going up and down, so I will just push it all the way to 3600 Hertz. And then the question will be, what is the range? Okay, so I'll first do the basic thing. Let's go from 500 to 3000. And then what I have is two carriers. So one of them is the triangle, which will run at the A frequency. Okay, and then the question will be, how do I combine them? Well, plus is obviously the mixing without interference. So I will combine it with the square wave. Let's get a lot of nice aliasing as well. Non-band limited square wave with the A frequency. So actually this already satisfies the description. And now you hear what is the effect of having quite high frequency of random values being selected, right? Because actually you can consider this being an engine that selects random values between 500 and 3000, 3600 times per second. So it's actually a really noisy thing. Let's hear how it will drop to drifting. If I do AR, so we started from 3600, want to drop down to 1 in 20 seconds. Okay, so what happens here is that actually I'm not really seeing all the possible parameters. Any ideas what's going on here? So I have one modulator, right? Well, right now I'm dropping the modulator frequency, so that would be one parameter. How about modulation depth? Well, the thing to note is, do I have modulation depth parameter here? No. What do I have instead? What is the modulation depth here, actually? Yes, it is the size of the range, so it's 2500. That's my modulation depth. But you see, the thing is that actually I could have different modulation depths for different carriers, right? So you see that the modulation depth, although it says modulation, it kind of refers to what goes to the carrier. right? And what is the third parameter? So every time we look at FM, we have 3 parameters. The third one is carrier frequency. I don't have it as an explicit parameter, but what is it now?
Frequency of the noise.
No, that's still the modulation frequency. The carrier frequency is actually the middle of the range, the middle of the modulator range, right? So those were the 3 things. First, I was specifying modulation frequency, minimum value, maximum value. That's what's here. But I could also specify modulation frequency, modulation depth, carrier frequency. These 2 sets of parameters can be matched. And then the third one, which is the more advanced one, which I discussed yesterday, was harmonicity, index of modulation, and carrier frequency. Okay, so in all 3 cases, we have 3 parameters, and each set of 3 parameters can be matched. Okay, so it is always the question of what I prefer. So actually, now I understand that it might make sense to do the ranging separately for the 2 carriers. So I can say, let this one run in the range of higher range, let's say 700 to 2000, and let's have this one run in the range, lower range, let's go bass. Well, actually this will be more like ticking. Let's do it the other way around. Let's make this more bass-like and make this one more nearer the high end. Okay, looking good. Not looking good. What am I doing with the brackets here? So I'm taking this. Okay, so this is one oscillator. Okay, and this is the second one. Looking good. Okay, let's try it with LF noise too. I'm not really liking every aspect. Okay, fun enough. Okay, so let me just put this aside. I will ask you for next week, which is our last week, by the way. For next week, I will ask you to draw this. Okay, so you will trace it on the video. But I would like to just modify this slightly to do something funny. So first of all, in this case, the modulator signal is actually an audible signal, at least for the beginning of it, because I actually have this LF noise. Okay, so this is actually my modulator signal. So I'm going to do something really funny, I hope. And what I'm going to do is I'm going to take the bandpass filter and I'm going to filter the modulator signal, but I'm going to do the frequency modulation of the bandpass filter with the modulator signal itself again, just with a different range. Okay, and here I'm going to have a low pass filter, and I'm going to do the same. I'm gonna filter the actual modulator signal, and the filter frequency will also be derived from the modulator signal, but scaled up. You see, this is why it's useful, because at this stage, signal A is a bipolar signal going between -1 and +1. So it's actually audio signal. You see, I use it here for the first parameter, which is the input for the filters. But then I take the same signal and I scale it up, I range it up into two different ranges and use that as a modulator frequency for these signals. Cool. Let's see what happens with the high pass filter. I want a bit more crackle in there. Cool, I really like that range. Let's go down to, what could it have been, 300? Okay, and now I would actually like to avoid this dropping thing, but I want it to move in this range. So I'm gonna take a noise signal, maybe 2 Hertz, and then range it from 3600 to 300. What did I mess up? Noise range. I left noise. Oh yeah, I need a letter there. Well, let's get it jumpy. Let's see what it does. And this bandpass filter, I think it makes me not like it. Cool. So I hope that's inspiring and forward, showing. It's a bit of a pain to go through the theory and the underlying, technical stuff, but it's the only way that will set you ready for some serious experimentation and discovering stuff. Because if you don't go through this path, then you will just be playing with the toys that you are given, which is good fun most of the time, but I imagine there is some motivation in you guys to actually figure out the toys and break the toys and make your own toys. So we're definitely on the right path. I will ask you to look at the video material, try to code this, do the exercise again, even if you've seen the solution once. There is a reason why we call this a programming language, and it relates to a language because, I don't know, well, you've learned a foreign language, one at least. The first time when you need to talk it's very difficult to start speaking. It's a very large threshold before you feel confident enough, before you get, a response from the medium that is worthwhile. Because if you get only error messages start to, what is the error, all of these things. It's, it takes quite some investment initially with, good faith that, it's gonna work out, you're gonna get there. But once you get there, the universe opens up seriously. Okay, so yeah, see how much you can do in this week before the next, and then also think about how you want to take exams. I mean, I didn't hear anything concrete from any of you guys yet, and I have an idea. So we're gonna discuss this because there will be a week in December. The first week of December, where I will be back, and then we can actually do a decent exam as well. Okay, cool. Thanks for being here, and I'll see you next week.